and welcome to this particular session of electricity and magnetism. The unit code is BPY1103, and my name is Moses Nderitu. I will be taking you through this first lesson in a series of lessons that will culminate into us going through the unit Electricity and Magnetism 1. It is Electricity and Magnetism 1 because we will have Electricity and Magnetism 2 amongst many other units that you will do as physics students. And having said that, I want to introduce to you the concept of electricity and magnetism. The reason being that electricity and magnetism go hand in hand. Electricity produces magnetism, and magnetism can produce electricity. And therefore, that is why this unit is taught as one, electricity and magnetism, as the most, if I would say, the most basic part of electricity and magnetism. This is what we shall be doing in this particular unit, and therefore I will introduce you to various aspects that we shall be looking at. Some of them I would introduce you now to what we refer to as the concept of charge. You will notice that as early as 1600 BC, Greek philosophers knew that when you rub plastic, and I would like you to do this with me, that you pick a plastic pen, especially a big pen, rub it against your hair, and you'll notice that it will pick small pieces of paper. Now, this, amongst many other experiments or many other demonstrations, indicate the presence of charge. Now, they also knew that there is a mineral magnetite that could attract other pieces of iron. That is to say that this science of electricity and magnetism was, and also electromagnetism, was founded on this foundation. Now, some of the early pioneers of this subject include Michael Faraday, and we know Michael Faraday because of the many things that he did in as far as electricity is concerned. We know that the Farad was named after him. And also another scientist, that is John Clerk Maxwell. We know Maxwell from the many things that he did in as far as electricity is concerned. We know that he developed what we call as the Maxwell's rules. Now, we also have Charles Augustine Coulomb. The name Coulomb, that was named after him. The unit of charge was named after him. These are some of the scientists who did quite a lot in as far as electricity and magnetism is concerned. Others who came recently include Heinrich Hertz. The name Hertz, H-E-R-T-Z, is the unit of frequency that was named after Heinrich Hertz. As others include Albert Einstein, and of course amongst many others who came after them. Now, this is just the basics to indicate that there are quite a number of things that has been done in as far as electricity and magnetism is concerned, and that brings us to what we know currently, that if you walk on a dry carpet, on a dry day, sunny day for that matter, you will accumulate charge such that when you go to hold a metallic knob, you might attract a spark. Maybe you have noted this in your day-to-day life, and this is just another way of demonstrating the accumulation of charge. Now, lightning, that we all know that happens during very rainy days, is a very large amount of charge that accumulates in clouds when they are moving in air. Remember, when clouds are moving in air, there is a lot of friction that happens between the clouds and air, and that makes them accumulate a lot of charge. And when clouds move along, come close together, there is, if they are oppositely charged, there is a possibility that a very big amount of charge can move from the clouds to the ground. And that is a very huge amount of charge that can actually be fatal. We have had cases in our country where people have been struck by lightning. The lightning strikes them because lightning is actually electricity, flow of charges. So when the flow of charges flow through their body, because of the fact that their head is pointed upwards, and remember, charges flow easily through pointed areas, and that's why it is not advisable to take refuge under a tree during a rainy day, because there is a possibility that as the cloud passes above there, and because of the fact that the tree is pointed, there is a possibility that lightning can easily pass through that tree, and if you are underneath there, you can easily get struck, and that can be very fatal. And that's why we are saying that it is not advisable to take refuge under a tree during a rainy day. This is just a demonstration of the concept of charge. And now, why do we say a body is charged? We say a body is charged if there is an excess of some of the charges, either positive or negative, in the body. Otherwise, a body is said to be neutral because of having equal number of positive and negative charges in the body. It will be neutral because the negative charges and the positive charges are equal in number, and therefore it is electrically neutral. And now, we know rubbing, as we started by mentioning that if you rub a big ball pen against your hair, it will become charged. Rubbing causes the transfer of charges from one body to another, between bodies. And if you rub a grass rod, if a grass rod is rubbed with silk, it becomes positively charged. And if a plastic rod is rubbed with fur, it becomes negatively charged. Now, charged bodies exert force on each other. That is to mean that if you have a positively charged body and another positively charged body, if you bring them close to each other, they will repel, they will push each other away. If it is positively charged and positively charged, it will push each other away. And if we bring together two bodies, one that is positively charged and another one that is negatively charged, we will notice that there will be attraction. There will be a force, but this time it will be an attractive force. They will attract each other. In other words, each one of them will experience a force of attraction because of the other. And therefore, I will now mention or take you through how it is to charge a sphere by induction. And this is very important, that supposing we are using a negatively charged ebonite rod and we want to charge a sphere using the ebonite rod. These are the steps that we need to carry. These are the steps that we need to carry. Number one, we bring the ebonite rod close to the sphere, and then we will notice that because it is negatively charged, the positive charges will be attracted to the end close to the ebonite rod, while the negative charges will be repelled towards the other end of the sphere. And remember, the sphere is insulated. Insulation makes sure that it is not in contact with the ground, because if it is in contact with the ground, then there will be discharge from the sphere through to the ground. Now, the negatively charged rod will ensure that the positive charges are concentrated on one end of the sphere, while the negative charges are concentrated on the other end. Now, step number 2 is where now you add or you ground the wire so that you can connect it to the ground. The reason is that you want to give the negative charges a way through which they can flow, and that is to mean that they will flow into the ground, leaving an excess of positive charges attracted on the end that the ebonite rod is. Now, the other step is to remove the ebonite rod. And those steps must follow each other in that order. Once you do that, you notice that because of the positive charges that were in excess, then the sphere will become positively charged. Can I mention this? That you must follow those steps strictly like that. Step number 1, bring the ebonite rod. The positive charges will be repelled. The positive charges will be attracted. The negative charges will be repelled. And then step number 2, while the rod is still in position, add the sphere. When you add the sphere, negative charges will flow into the ground. And now, once you add, remove the earthing. Remove the earthing, because if you don't remove the earthing, and now you remove the rod while the earthing is still there, then it will mean that negative charges will flow back and neutralize the sphere, and therefore you will not have achieved the objective of charging the sphere positively. And therefore the steps has to follow that order strictly. Bring the ebonite rod close to the sphere, positive charges are attracted, negative charges are repelled. While the rod is still in position, add the sphere and then remove the earthing while the rod is still in position. And then the last step is to remove the rod, and now the positive charges that will have been attracted on one side of the sphere will now be released to spread through the whole sphere, and therefore you'll have achieved the objective of charging the sphere using a negatively charged rod. You could do the same using a positively charged rod, and the process is the same, only that now the negative charges will be repelled, positive charges, negative charges will be attracted, positive charges will be repelled, and the process will be the same. And you can do that. You can do that as part of your homework. Now, I want to bring to explain to you how we go about charging a sphere by contact. Just like the word suggests, when you do you use the contact method, we are referring to actually what we call as conduction. So basically what we mean here is that we will use the ebonite rod again, and since the ebonite rod is negatively charged, when you do a contact with a metal sphere, what you'll realize is that the negative charges will flow into the sphere, because already if the ebonite rod is negatively charged, it means it has excess negative charges in it. And if it has excess negative charges in it, then it will mean that the negative charges will flow into this metal sphere, and that will mean that the negative charges will now charge the metal sphere, and it will charge it negatively. Remember, it was negatively charged. It has now been the negative charges have flown into the sphere, and therefore the sphere will end up having a negative charge. Now, there is a way in which we can still do and charge two spheres one positively, one negatively, to the same quantity using one charging rod. How do we go about that? This is what we do. We bring two spheres close to and in contact with each other. The two spheres are in contact with each other, and now we introduce a positively charged rod. When we introduce a positively charged rod, we will notice that the negative charges, because this is positively charged, the negative charges will be attracted to one end of the sphere, and the positive charges will be repelled to the other end of the other sphere. The reasoning being there is contact between the two spheres, and because there is contact between the two spheres, we will notice that negative charges from this sphere have a way of going through to the other sphere, while positive charges in this sphere has a way of going through to the other sphere. And now, because of that contact, and because we are using the same charging rod that is positively charged, and remember, it is not in contact. It should not be in contact. It should be close to but not touching. Because of that, the negative charges will be attracted to one end, the positive charges will be attracted, repelled to the other end. While we still retain the charging rod at that point, we will notice that if we pull them away using the insulated part, remember, you shall not touch the sphere, because if you touch the sphere, then basically what you are doing is to discharge the sphere, and therefore you should not touch the sphere, but you should touch the insulation part, that part that is insulated. Now, at that point, with the positively charged rod in position, pull one sphere away from the other such that there is no contact in between them. That is to mean that one of them has excess positive charges and the other one has excess negative charges. And this is to mean, therefore, because of this excess negative charges and this excess positive charges, it will mean that if we withdraw the charging rod, the sphere that had excess negative charges remains negatively charged, and the sphere that had excess positive charges remains positively charged because it has excess positive charges. And therefore, we will have achieved the objective of charging one sphere negatively and the other sphere positively to the same quantity, and that will mean that we will have achieved the objective of charging spheres by induction, and therefore that will have been achieved. Now, there is a device that is used in noting whether a body is charged or not. That is what we refer to as a gold leaf electroscope. Now, a gold leaf electroscope is a device that has the following features. Number one, it has a brass cup. It has an insulator. This shaded part is an insulator. It has an earthed metal case. This metal case, the whole of this is a metal case that is earthed. It has a brass rod, this one, and it has a gold leaf, this one, the thin line, and the brass plate is this one here. This is what we refer to as a gold leaf electroscope. This device that is found in most of our science laboratories in schools is used in showing whether a body is charged or not, and it can even be used to indicate the type of charge that a body has. Now, how do we go about charging an electroscope? We do the charging of an electroscope in this way. If it is not charged at all, then the leaf will have collapsed. The leaf will be lying on the blast plate and it will have been collapsed. If we want to charge by contact, then we notice that the negatively charged rod, you will need to place it on the cap of the electroscope, and because it is negatively charged, meaning that it has excess negative charges, then the negative charges will be attracted by the plate, the rod, and the leaf, and the plate. And because they will be transferred into the cap or into the electroscope through the cap, if you remove the negatively charged rod, then the electroscope will become negatively charged. The electroscope will become negatively charged, and therefore it will have achieved, or it will have gained the negative charge. Now, if we want to charge it, if you want to charge by induction using the same negatively charged rod, you will bring the rod close to the cap but not touching the cap. Notice the difference. For contact method, you touch the cap using the rod, but for induction, you don't touch the cap, you bring the rod close to but not touching the cap. Now, once you do that, what you'll notice is that negative charges will be, because this is negatively charged, the rod will be negatively charged, positive charges will be attracted to the metal cap, and because of the negative charges that are within the rod, the negative charges will be repelled to the leaf and plate. And that is why when you bring the negatively charged rod, the leaf will diverge. We call it as diverging or converging. When it is when the angle is increasing, we call it as diverging. When the angle is reducing, or we call it as converging or collapsing. Now, when you bring the negatively charged rod close to the cap of the electroscope, then the leaf will, and that is to mean that there will be more excess negative charges here, while there will be excess positive charges at the plate. Now, while the rod is still in position, that is step number 2. With the charging rod still in position, you add the cap. You add the cap. Adding the cap will mean that the negative charges that were at the plate and leaf will flow through to the earth, and the moment they flow through to the earth, the leaf will collapse. As you can see, the leaf will collapse. Now, once you remove the charging rod, remember, as at that point, we have, because negative charges have flown through to the earth, we have an excess of positive charges on the plate. While the rod is still in position, excess positive charges are on the plate, and therefore, the moment you withdraw the charging rod, what you'll notice is that the positive charges that were on the cap will now be distributed through the whole, the cap, the rod, and the plate and leaf, and therefore you will notice a divergence in the leaf. The gold leaf is so thin and light such that it will just diverge if it is charged, because there will be repulsion. There will be a repulsive force between the plate and leaf. And that is how we obtain the objective of charging an electroscope, either by contact method or by induction method. You will notice that in my two presentations, that is when we are charging through the contact method using the negative charge sphere and using the induction method using the negatively charged sphere, that the electroscope attains opposite charges. That means when you are explaining to your students, you will need to explain to them that it is not, they need to be careful which method they are referring to, because you'll notice that we have used the same charging rod but two different methods, and what we obtain is one electroscope using the contact method is negatively charged, and using the same negatively charged rod, the other electroscope becomes positively charged. And therefore, it is very key that when you are explaining to students, let them understand, let them know the difference or what they need to do, or rather what results they achieve when they are using one method as opposed to the other method. It's very key and very, 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 very important that you explain that to them. Now, these are the steps. These are the steps in charging an electroscope by induction. Step number one, you bring a charged rod close to but not touching the metal cap. What you'll notice is that negative charges will flow into the rod, the plate, and leave. While the rod is still in position, that is step number two, add the cap. Add the cap. The negative charges will flow through the earthing. And notice here that you can even use your finger to do the earthing, because your body is a conductor. You can use your finger to do the earthing while the charging rod is still in position. Then, once you do the earthing and remove it. Remove the earthing. Once you remove the earthing, you will notice that there will be excess of positive charges on the plate, excess charges on the cap, and excess positive charges on the cap. And then once you withdraw the earthing, or rather the charging rod, you will notice that in step number 4, the electroscope will be positively charged. I would wish that you use not a negatively charged this time round, not a negatively charged rod this time round, but use a positively charged rod. Explain the steps that will follow until you achieve the final product, which is a charged electroscope. Will it be positively charged? Will it be negatively charged? And what are the steps? I'd like you to do that, and then we can discuss it through the online platform. Now, all the experiments, all the demonstrations that we have done, all the steps that we have mentioned are pointing at the following very key points. Number one, that there are two types of charges. That is, they are called positive charges and negative charges. And we have also seen a very important observation that like charges repel, while unlike charges attract. Like charges repel, while unlike charges attract. We have also seen, very key, that electrostatics is the study of charges, and these charges must be at rest with respect to each other, or if they are moving very, very slowly. Now, we have also seen, very key, that conductors allow flow of charges, while non-conductors do not allow flow of charges. We have seen that conductors allow flow of charges, while non-conductors do not allow flow of charges. Examples of conductors include metal. The most obvious example would be metal. Tap water is also a conductor. The human body is also a conductor, and many others. There are many other conductors that we have. Examples of non-conductors will include glass. They will also include plastics, among many other examples. I would like you to tell me in the university portal, what are semiconductors? What are they, and what are some of the examples of semiconductors that we have? I know you can do that because I know you can do your research, and I would like you to do that so that you give me the answer in the University Students Learning Portal. I would like now to introduce what we refer to as the Coulomb's law. Now, Augustine Coulomb, remember we mentioned him in our introductory statements, that he lived between the year 1736 and 1806. And Augustine Coulomb conducted quite a number of experiments. And one of the key experiments that he conducted is the force that exists between two bodies, two charged bodies. What is the force that exists between them? He noted that the force that exists between two charged bodies is directly proportional to the charge of the two bodies. That is, the force is proportional to the product of the charges, that's Q1 and Q2. He also noted that there is an inverse relationship between the distance of separation of the two bodies. The longer the distance, the less the force, and therefore he said that the force will be proportional to the inversely proportional to the distance of separation. That is, F is directly proportional to 1 over r squared. And therefore, when we combine the two, we notice that the formula will lead us to F is proportional to Q1, Q2 over r squared. A very key finding that was discovered or worked on by Augustine Coulomb, that tells us that the force that exists between any two charged bodies, Q1 and Q2, is directly proportional to their product and inversely proportional to the square of the separation distance. That is to mean, the more the distance of separation, the less the force of attraction. The smaller the distance of separation, the more the force of attraction. But the force is directly proportional to the charge between the two. That is, F is directly proportional to Q1, Q2. Now, if we remove the constant of proportionality, we introduce a constant K, where K is the proportionality constant, and this formula is the Coulomb's law, and it holds for all point charges whose size is much smaller than the distance between them. And now, in SI system, the constant K is expressed in the form K is equal to 1 over 4 pi epsilon naught, where epsilon naught is approximately equal to 8.85 times 10 raised to power minus 12 Coulomb squared per Newton meter squared, which is the permittivity constant. When you work out these values, since epsilon naught is known, it is a figure, and pi is a value 3.14. We know the value of pi, and 4 is also a constant. What we will notice is that K is equal to 8.99 times 10 raised to power 9 Newton meter squared per Coulomb squared. Now, I would like you to, during your free time, look at the Newton's law of gravitation, which is F is equal to G m1 m2 over r squared, and compare that with the Coulomb's law, which is F is equal to K q1 q2 over r squared. Notice that the Newton's laws had been there about 100 years by the time Coulomb was doing his experiments. Notice the similarity and think about this discovery and what probably Augustine Coulomb may have felt when his discovery was close to what Newton had already done and which had been in existence for quite a number of years. The Coulomb's law in vector form, if we consider 2-point charges Q1 and Q2, and these charges are separated by a distance r12, such that F12 is the force exerted on the charge Q1 by charge Q2, and R12 is the separation distance between them. Now, what you notice is that if these two charges have the same charge, then the force that will exist between them is repulsive. In other words, they will repel each other. And that's why the force is existing such that F21 is outward and F12 is outward. That means there is, they depict that there is a repulsive force between them. And now, because they are both having the same charge, that is why F12 and F21 are in opposite directions. But supposing one is positively charged and one is negatively charged. Remember what we said about oppositely charged particles or bodies? They will be experienced an attraction between the two bodies, and therefore what you'll notice is that there will be an attraction between F1, Q1 and Q2 such that the force 2-1 is in this direction while the force 1-2 is in that direction, and therefore they will be such that, unlike when they are equal, having the same charge, the force is repulsive. But when they have opposite charges, one is positive, the other one is negative, there is attraction, and that's why the forces are antiparallel to R12. And therefore, the position vector of the point charges Q1 relative to the vector Q2 is denoted as R12 with a unit vector R cap. Notice the cap, R cap 1, 2. It is a unit vector, therefore the magnitude is 1. In other words, even if we were to multiply that with the formula that we had, it would have no effect magnitude-wise, because the magnitude of R12 cap, the unit vector R12 cap, is 1. The magnitude is 1, and therefore there will not be any change in as far as the value is concerned. Now if 2-point charges have the same sign, then the force 1, 2 is repulsive and must be parallel to R12, as we have mentioned. Now, if the charges are opposite, therefore the force will be attractive, and therefore it will be antiparallel to 1, 2. Now, from the formula, the Coulomb's law that we mentioned in an earlier slide, F12 will therefore, in vector form, will be equal to K, the constant K, 1 over 4 pi epsilon naught, Q1, Q2 over R squared, R12 squared, multiplied by the unit vector R12, where R12 is the magnitude of R cap 1, 2. Now, similarly, the force exerted on the point Q2 by charge Q1, we are only changing to now see the magnitude of the force exerted on the point charge Q2 by charge Q1, and it will be given by F21 is equal to K, Q1, Q2. Those are the same. The distance is the same. It is not changing. Multiplied by r21, that is now the vector 2, 1, whereby it is only that it's changing from 1 to 2, 1. But remember, it's a unit vector, and therefore the magnitude of that unit vector will be equal to 1. Now, I would like you to look at this particular example. Now, consider 2-point charges, Q1, which is negative 1.2 microcoulombs, and Q2, which is positive 3.7 microcoulombs, and they are separated by distance R12, which is 15 centimeters. Calculate the Coulomb force experienced by the charge Q1 due to the charge Q2. In other words, I would like you to use this formula and use the value Q1 and Q2 and R12. Remember, it is in centimeters. You must convert it into SI units all the time. Every time you are working on a physics problem, it's always advisable to ensure that you convert the units given to SI units. Like this microcoulomb, you must convert it into coulombs. 3.7 microcoulombs, convert it into coulombs. And you'll find the answer in the e-learning platform of Mount Kenya University, which I believe you can check at a convenient time. Now, I would like at this point to introduce to you the lines of force for electric field. Now, lines are used in visualizing the electric field. In other words, they are non-existent. They are not there literally, but they are only used to visualize the electric field. Now, they are referred to as lines of force or electric field lines. Now, there are two distinct features that we see in electric field lines. Number one, that they indicate the direction of the electric field. In other words, they show us where the field is coming from and going to. Now, number two, they originate from the positive charges or charge and terminate on the negative charge or charges, as will be illustrated in figure 1.5, which is in the next slide. I will show you the next slide, and I'll show you what I mean by these two particular features. And I would like you to do this. Because I have not done that for you in the next slide, I would like you to draw lines of force for a negative charge point, a negative point charge, and also draw the lines of force for two negative charges that are close to each other. Now, notice that the lines of force are drawn such that the number of lines per unit cross-sectional area is proportional to the magnitude of the field lines. In other words, the closer the field lines, the stronger the force. The closer the field lines, the stronger the force. The farther away the field lines are, the weaker the force. That is key. You need to remember this particular point because it is key for you to remember that the closer the lines, the stronger the force. The farther away the lines are, the weaker the force. That is key. You need to remember that. Now, as we had mentioned, lines of force originate from the positive charge and they end at the negative charge, as will be indicated by these unlike charges close to each other. If we are to draw lines of force, we will notice that lines will originate from the positive end all through to the negative end. That is, the arrows will indicate that they are coming into the negative charge. Now, because of attraction, there will be a lot of force of attraction between these two, and therefore the lines of force are close to each other, and therefore they will indicate that there will be a lot of force. Remember, we said that the closer the lines of force, the stronger the force. The closer the lines, the stronger the force. Now, if you bring two positively charged, positive point charges close to each other but not touching, you'll notice that charges will, or rather lines of force will be drawn such that they are originating from the positive charge outward and positive charges outward. Notice that there are not lines of force in between here like we had in this particular case when we had a positive charge and a negative charge. The reasoning here being that there is no attraction between these two. Remember, they are both positively charged, and therefore the force that exists between them is repulsive. And because of that force that is repulsive, that is why there are no lines of force that are existing between these 2 point charges. And therefore, it's very important for us to remember that in this particular case, lines of force are originating from the positive end, but they are moving outwards, just like in this particular case. Now, this is what I would like you to do, the assignment that I had given you in the previous slide. We have used a positive charge, now use a negative charge. We have used 2 positive charges, now use 2 negative charges, and indicate the direction of the field lines. Indicate the direction of the field lines when we have 2 negative charges. Now, having said that, I would like to introduce to you the concept of capacitors. You will notice that as early as 1745, as early as the year 1745, quite a long time ago, a German scientist had found that a volume of water in a glass jar could store charges if some high voltage is applied to a wire in the jar. In other words, he had already noted that should you apply a voltage, a high voltage to a wire in a jar that contains water, that jar could store charges. Now, a year later, a Danish physicist invented a similar device that was used to store charges. That is, he named it the Leyden jar because he named it after the University of Leiden where he was working. He called it the Leyden jar to associate it with the University of Leiden where he was working. And therefore, the Leyden jar that I will be showing you in the next slide is made of a glass jar, and it has a tin foil lining and a brass rod terminating in an external knob at the top of the jar. And now, when an electric charge is applied to the knob, we notice that positive and negative charges accumulate in the metal coating of the glass jar, and therefore the Leyden jar was found very, very useful in applications to store electricity, in experiments, and also in early wireless equipments. We notice because capacitors have the capability of storing charge, then in experiments, in wireless experiments that in experiments that required storing of charge, and also wireless equipment that required storing of charge, the capacitor was found to be very, very useful. Now, this Leyden jar, which is a demonstration of what capacitors can do, are such that it has a metal rod, it has an insulation, it has a positive charge. When it is fully charged, this part will be positively charged. When it is fully charged, this part will be negatively charged. It has a tin foil, both inside and outside, and also a wire. If it is charged, it was found to contain or to carry charges with it, or to store charges with it, which could be used in another experiment. Those charges could be used in another experiment, and therefore that is why it was found very useful. One, for experiments that required storing of charge, and number two, for experiments that required, for devices that requires storing of charge. Very, very useful, and it was one of the devices that was discovered that would later culminate into the capacitors that we have currently that are used in radios, televisions, computers, and so on and so forth. Now, therefore, what are capacitors? Capacitors, therefore, are devices that store electrical energy. In other words, they are devices that are deliberately used to store charge. In other words, when it is fully charged, it can store charge on its own for a very long period of time. And I would wish to mention at this point that it is advisable that teachers of physics will mention to students that even if they were to find an old electrical device, like an old television, an old electrical device, or an old device that has capacitors in it, it is very, very important to ensure that you do not touch any capacitor, because it could still be carrying a lot of charge even if it is not connected to any electricity. Even if it has been there for a long period of time, it could still be carrying a lot of charge. That sometimes some of those charges could actually be harmful, and because the moment they discharge through the body, they could actually be very, very harmful. And that's why it is very key, because of this fact that capacitors are used to store electrical energy. It is very key that you advise students that they should not touch capacitors anyhow, all old electrical devices anyhow, because they could still be having a capacitors that have a very high capacitance that could still be carrying charge over a very long period of time. Now, if we have, therefore, what are conductors? If we have two conductors that are separated from one another and their surroundings, they form a capacitor. It doesn't matter the shape. A capacitor is simply one plate, another plate, and they are called plates regardless of the shape. A capacitor is just a plate and another one. There could be a material in between or not, provided there is a plate and another one, and of course a wire and another one. That forms a capacitor. It doesn't matter the shape. It forms, that will form what we are referring to as a capacitor. Now, and one key point that we need to remember is that when a capacitor is charged, the conductors carry equal and opposite charges, right? And why we are saying they carry equal and opposite charges is because when you charge a capacitor using a battery, for example, one capacitor will gain positive charges. One part of the capacitor, one plate of the capacitor will gain positive charges. The other plate of the capacitor will gain negative charges. But these two charges, the positive and the negative, will be of the same magnitude. And therefore, electrically, a capacitor will have zero resultant charge. Why? This is positive charges. Let's take an example, positive 5, and this will be negative 5. Combined, 0. Therefore, it will have equal number of charges, right? And therefore, note that Q is not the net charge. Yeah, it is not the net charge on the capacitor, because the net charge is 0, since the plates carry equal but opposite charges, right? A capacitor can be charged by connecting the two plates to opposite terminals of a battery. As we have mentioned, that if you have a capacitor
connect one to the negative end of the battery and the other one to the one positive, one negative end of the battery. After that charging takes some time, then you withdraw the charging agent, that is the battery of the cell, then you notice that the capacitor will be charged. It will have charge, and even if we withdraw the charging agent, it will in itself carry charge. It will in itself carry charge, and therefore, very important that we realize that the net charge is 0. Now, in charging the capacitor, the battery transfer equal and opposite charges to the two plates. A battery will transfer equal and opposite charges to the two plates. One positive, one negative, but equal in number. For example, positive 5, negative 5. Equal number because we are using the same battery or the same cell. Now, that is to mean that at the end of the day, the net charge will be 0. Now, the potential difference of the battery appears across the plates. The PD across the plates, the PD of the battery will appear across the plates. Now, the magnitude of the potential difference is represented by capital V and is directly proportional to the magnitude of the charge Q on the capacitors. That is, how much charge we gain will depend on how much voltage we use, right? How much charge we gain on the capacitor will depend on how much voltage we have applied on the plates of the capacitor. In other words, Q is directly proportional to V. The more the voltage we apply, the more the charge we gain. And therefore, Q is equal to CV, in which C is the capacitance of the capacitor. Now, this is an important formula that we will keep using as time goes by. Now, capacitance is therefore a constant, and it depends on the geometry of the capacitor. Capacitance is a constant that depends only on the geometry of the capacitance. The SI unit of capacitance is the farad. However, you notice that this farad is such a big value that we actually don't use the farad in all the devices that we have. We use microfarads, a very small amount, because we only need a small amount of capacitance. Therefore, the farad is such a huge amount of capacitance that we rarely actually never uses. You may never find a device or a capacitance that has 1 farad in your lifetime. You may never find one. Now, 1 farad is 1 coulomb per volt, which is the same as 1 C over V. Now, the farad was named after Michael Faraday. Remember, Michael Faraday is one of the scientists whose scientific work dealt so much on electricity and magnetism, and therefore the farad was named after Michael Faraday because he is one of the pioneers who developed the concept of the concept of capacitance. And therefore, this is a key formula that we shall be using. You can manipulate it either to calculate V to get Q over C, or to calculate C to get Q over V, depending on what it is that you want. You can manipulate the formula to suit the kind of thing that you are doing and what it is that you want to do. Now, as an example, which I would like you to calculate, a storage capacitor of a random access memory, that is RAM chip of a computer, has a capacitance of 55 picofarads. If it is charged to 5.3 volts, how many excess electrons are there on its negative plates? Now, you can see this answer in the MKU e-learning portal. Now, electrical devices should be kept clean. And that is why you notice that the computers that we use in our offices and even in our homes, and those that are used even in banks and all those other places, are kept clean, and time and again the maintenance team will come and blow those computers so that they can remove all the dust. That is the reason being that even a small speck of dust can carry a very huge amount of charge. If it is charged, it can carry a very huge amount of charge. And therefore, that is why it is very necessary to ensure that we clean electrical devices, because so that we can eliminate charges, or rather that can accumulate in dust, and some of them that can actually be harmful. Now, the electric field in a capacitor is related to the charge on the plates of a capacitor by Gauss' law. And Gauss' law states that epsilon naught, the integral of EdA, is equal to Q, or if we could integrate this with respect to A, or we get epsilon naught EA is equal to Q, in which A represents the area. A represents the area of the Gaussian surface through which the flux, or which we could simply call the field lines, passes. And therefore, A is the area. And therefore, that is the area that represents the Gaussian surface through which the flux, or what we call as the electric field lines, passes. Now, if the potential difference between the plates is related to the electric field E by the following formula, that Vf minus Vi is equal to minus the integral from I to F of EdS. Now, if we do this, if the absolute value, therefore, is denoted by negative V, if we denote the whole of this by negative V, then we'll get that negative, this negative here, will cancel with that negative, and therefore we'll get the integral from the positive end to the negative end of EdS. Now, the positive and negative signs just indicate that the path of integration starts on the positive plate and ends on the negative plate. That's simply what the positive and the negative end indicate. That the path of integration starts on the positive plate and ends on the negative plate. And the electric field between the plates of a capacitor is the sum of the electric fields due to the plates. In other words, for us to get the electric field between the plates of a capacitor, we need to get the sum of the fields due to the plates. So we have been talking about a capacitor, but if we can give us an example of a parallel plate capacitor, the parallel plate capacitor, it has the plate that is positively charged, a plate that is negatively charged, and notice that the number of positive charges and the number of negative charges are equal. This is in the case where there is no material in between the two plates. The area of the capacitance is A, the area of the capacitor is A, and the distance of separation of the plates is D. The distance of separation of the plates is D. Therefore, we notice that the parallel plate capacitor will have a positively charged plate, a negatively charged plate of area A. Remember, the two plates must be the same area, A, and the distance of separation is D. Now, notice that we have talked about the air. Why are we indicating that this is air? Because there are possibilities where instead of air, we put a material in between them. That material is called a dielectric, and we shall be mentioning it as we move along. Now, consider a parallel plate capacitor where the plates are large and close together. The distance of separation is small, but they are large enough and they are close together. Therefore, we can mention at this point that the Gaussian surface encloses the charge on the positive plate of the capacitor. The magnitude of the electric field is given by E is equal to Q over epsilon naught A, and therefore the potential difference, remember using the formula that we saw previously, it will be V is equal to the integral from the positive end to the negative end of EDS. But because we know E as Q over epsilon naught A, then this is going to be the case whereby V is equal to the integral from the positive end to the negative end of EDS, which is equal to Q over epsilon naught A, the integral of from 0 to D ds, which is equal to, once we integrate ds with respect, once we integrate this part with respect to s, we will notice that, and then we substitute for the value of d, we will get qd over epsilon naught A. Now, since V is equal to Q over C, remember the formula that we saw in an earlier slide, that Q is equal to CV. Therefore, manipulating this same formula, you get that V is equal to Q over C, and therefore we will get from this formula. Therefore, we can manipulate them and see that C is equal to epsilon naught A over D, and this is therefore going to say that the capacitance of a capacitor depends only on the geometrical factors, namely the area and the distance of separation. In other words, a capacitor, if you want to know the capacitance of a capacitor, all you need to vary is the distance of separation and the area of the capacitance and the distance of separation. So, in other words, it's possible for the manufacturers to calculate the capacitance by determining what area it's going to be. Of course, the value of epsilon naught is constant, it's known. So knowing this, if you vary the area, how much area of the conductors that you use, it can give you the capacitance of the capacitor. Therefore, this is the formula that connects the capacitance, the area of separation, the area of the capacitance, and the distance of separation. Therefore, for us to determine the capacitance, all we need to know is the area and the distance of separation. That is key when it comes to the manufacturing of the capacitors. Now, I will introduce to you the energy stored in an electric field. Now, supposing we consider a parallel plate capacitor, and we say, for example, that at time t, a certain charge Q has already been transferred from one plate to the other. All right? We assume that during the charging, after a certain time t, remember, for us to charge the capacitor, we connect the terminals of the capacitor to a charging agent, a cell or a battery, and then we give it some time. Let's assume that after time t, the charge Q has already been transferred from one plate to the other. Now, the potential difference V prime, notice the prime, between the plates at that moment is V prime is equal to Q prime over C. Now, supposing we have an increment of dq that is transferred, which results to a small charge du in the electric potential energy. In other words, du will be equal to V prime dq, and that will mean that will be equal to Q prime over C. Remember, from the formula of V prime we get Q prime over C dq, and because we can integrate this, we have that V prime is equal where V prime and Q prime denotes the instantaneous values. That is the small amounts of voltage and charge that accumulates over a small period of time after we have done the charging. And these are the values of the potential difference and the charge respectively. Now, having said that, if this process is continued until a charge Q has been transferred, the total potential energy U, it will therefore be equal to the integral of du, which is the integral from 0 to Q of Q prime over C dQ. And the moment we integrate that part with respect to Q, and between the limits 0 to Q, we will get that it will be Q squared over 2C. And using Q is equal to CV, we will get that U is equal to a half CV squared. Now, notice that this is a key formula that we shall be using when it comes to charges, when it comes to capacitance and the voltage that we are using to do the charging. Now, for capacitors with a dielectric material, remember I mentioned the term dielectric, and we said the dielectric material is the material that is placed in between the plates of a capacitor. Instead of having air in between the plates, we have a dielectric material, and the dielectric material can be maybe mica, it can be paper, it can be any material that will increase the capacitance, because as we shall see, a dielectric material increases the capacitance. Now, for a capacitor with a dielectric material, that is a material put in between the plates of the capacitor, the capacitance of the capacitor is altered. Altered in the sense that it is increased, it is made higher, it is made to be more. Now, the capacitance of the capacitor is altered. In other words, a capacitor with a dielectric material in between the plates has more charge than a capacitor without a dielectric material. In other words, a capacitor with a dielectric material will have more charge than a capacitor without a dielectric material. That is important. That is important to note, that the factor Ke, which is called which is defined as C over C naught. This is called the dielectric constant. C over C naught, it is called the dielectric constant, and it is the dimensionless factor, dimensionless in the fact that capacitance C is in farads, C naught is also in farads. Therefore, the moment you cancel them, it will mean that there will be no charge, there will be no net charge, and therefore it is the dimensionless factor by which the capacitance increases relative to its value C naught when the dielectric material is present. In other words, a capacitor with a dielectric material will have more capacitance than one without the dielectric material, right? In other words, it will have more capacitance. That's very key to note. And we have quite a number of types of capacitors, and these are what we refer to as air capacitors. Air capacitors are capacitors such that there is nothing in between the plates of the capacitors except air. In other words, the plates are separated by air. There is nothing in between. This is a type of capacitors that is mainly used in the tuning when we want to tune an analog radio. When I say an analog radio, the radios that we use to tune, you turn a knob, and then you tune in to a certain station. When you want to tune in to another one, you tune in using the same knob, you tune in to another one, and so on. It has an indication where you are there's a scale where the scale moves until it gets to a certain frequency. And then if you want to go to another frequency, you tune again, it goes to another frequency, and so on. Actually, what is happening inside the radio is that there is a capacitor that is air that has air in between. Now, what happens is that as you are tuning, as you are turning as you are tuning the radio, as you are turning, the area is either increased or decreased, and that is to mean I'll be showing you some of those air capacitors as we go along, and I'm sure because you may have had an opportunity to see an analog radio, you may have come across one. It is such that when you tune what I would call as the cogs or the teeth of the air capacitor interlock such that either the air is increased or reduced depending on the capacitance you are looking for. Remember, we said the capacitance of a capacitor depends on the area and the distance of separation. So if you want to increase the capacitance, you can increase the area. If you want to decrease the capacitance, you decrease the area. So by turning the radio, you are either increasing or decreasing the area of the capacitance, and therefore altering the capacitance, and therefore ensuring that the capacitor is to the capacitance is to the value that you want, and the radio gets tuned using that. And therefore, that is one of the types of capacitors that we have in use. Another one is the paper capacitors. That is, the paper capacitor has two plates, one plate here, and then paper in between. And then usually they are rolled. We have the plate and another plate, and then paper in between. Then the two are rolled and put in a container, and then the electrodes are connected that are used now to connect in an electric field, in an electric circuit, or even charging using a battery or a cell. So that is what we call as the paper capacitors. Now, they can have either paper, wax, or oil, and then they are rolled into a compact form. Now, there is also the mica capacitor. They consist of alternate layers of mica and metal foils and clamped together tightly. They are clamped together tightly so that they form what we are referring to as the mica capacitor. The ceramic capacitor is another type of capacitor, and it has an electrode which consists of metallic coatings which are usually of silver on opposite faces of a thin disc or plate or ceramic material such as silicate of magnesia. Another type is the electrolytic capacitor, which consists of two aluminum foils, one with an oxide and another one without, and interleaved with a material such as paper that is separated using suitable electrolyte such as ammonium borate. I will now show you some capacitors that we have in real circuits. In a circuit, you might come across a device that looks like this. This is actually a capacitor. You may come across another one that looks like this one. This one is such that it is indicated. The capacitance is indicated, and even the voltage that it can hold, or the voltage that can be used to charge it, is indicated. This one has actually a name, capacitor, on it, so it is easy for you to identify it in an electrical circuit. Others will be of this shape. This is the variable capacitor that I was mentioning a while ago, that is used in the tuning of a radio. You tune to increase or decrease the area, and therefore to alter the capacitance. this one here. This is also another variable capacitor, and others will have this shape. Others will be this shape, depending on the capacitance required. Others will be this shape, and so on. These are some of the capacitors that we have in electrical devices, and this is to mean that we have various capacitors in electrical devices. Now, I will now demonstrate to you how to combine resistors, not resistors but capacitors, either in series or in parallel. Why do we call this as a series connection? It is a series connection between these two capacitors, C1 and C2. Why? Because they share the same current. Current comes in through C1, passes through to C2, and out again to the external circuit. And that is why they are called as a series connection of capacitors. This is a parallel connection of capacitors because they do not share the same circuit, the same current. Depending on the value of the capacitance, the current will come in at that point, and then it will subdivide. Some of it will go up through C1, some of it will go down through C2. Then the currents again will combine at that point and leave again to go to the external circuit. So the connections of the capacitors is important in electrical circuits, because there can be situations where a device that is being constructed, maybe a computer or a laptop or a radio or whatever it is that is being constructed, would probably require a certain amount of capacitance. If that were to be the case, then we need to know if we need 3 microfarads, for example, which capacitor do we connect to which one so that it can give us that 3 microfarads. If we need a smaller capacitance, how do we connect them so that we can get the capacitance that is required? So the connections are key. We need to understand how to do the connections so that we are able to understand how we do the connections so that we can get to the value that we are looking for. I will show you a capacitors in an FM radio before we get to how to calculate the capacitance. This is an actual FM radio circuit with capacitors indicated. These are capacitors. This one is a capacitor, this one here, this one here, this one here, all right? These ones, all these are capacitors, all these ones, okay? So these are capacitors in a real FM radio circuit, and it is important that we know that they can be connected either in parallel or in series. They can either be connected in parallel or in series, depending on what it is that we are looking for. Of course, a radio, an FM radio circuit will contain other devices, like we have a tuning coil, an antenna, and DC 4.5 that is used to connect to the cells. It has a speaker terminal and so on. It has, of course, it has resistors, which we shall be discussing in the next slides as we go along. But it is important that we note that within this circuit, we not only have capacitors that we are discussing now, but we have other devices, the integrated circuit, and so on. But importantly, we have the resistors. The resistors are key, and we shall be discussing them in the subsequent slides as we go along. Now, we have mentioned about calculating the effective capacitance for parallel arrangement of capacitors. We said that when a current is released from the positive end of the cell, it will come to that junction and it will subdivide such that some of the current goes through C2, some of the current goes through C1, and then the currents will combine again at that point so that it can go back to through the circuit and so on, and the current goes on and so on and so forth. Depending on the capacitance of C1 and the capacitance of C2, we can have the subdivision of the current depending on where, or depending on which one has more capacitance than the other one. Now, for parallel connection like we have in this case, we notice that because C1 and C2 are both connected to the same voltage source, then Q1 is equal to C1 times V, and Q2, the charge on C2, is C2 multiplied by V. Why we are saying this is because the two of them are being charged by the same voltage source, and therefore the value of C1, which will determine how much current will flow through or how much charge it will have, and the value of C2, which will also determine how much charge it will accumulate, will be given by Q1 is equal to C1V and Q2 is equal to C2V, and the total charge will be the charge that will accumulate when we have a combined capacitance C1, when we have combined capacitance C, that is for C1 and C2 combined in parallel. What is that supposed to mean? It means, therefore, Q, which is the total charge, is equal to Q1 plus Q2, and therefore, and we know the total charge will be equal to the total capacitance multiplied by the voltage, and therefore Q is, which is equal to Q1 plus Q2, is equal to CV, and therefore implying that CV, which is the total charge, will be equal to C1V plus C2V. And remember, the voltage V is common, so we can cancel V throughout, and we are left with C is equal to C1 plus C2. In other words, if we want a very huge amount of capacitance, then we connect the capacitors in parallel, because the moment you connect the capacitors in parallel, the effective capacitance will be the sum of the two. In other words, the effective capacitance will be the sum of the two capacitors, that's C1 plus C2. Now, I'll give you an example that we will work out together. For capacitors in parallel, that is, maybe if we take C1 and C2 to be 2 microfarads and 3 microfarads respectively, we will notice that the combined, which we are calling as the total capacitance, will be given by CT indicating the total capacitance, which will be equal to C1 plus C2, which is the same as the algebraic sum of these two, C1 plus C2, which is 2 plus 3 microfarads, to give us a total of 5 microfarads. Now, that is as far as the combined or total capacitance when capacitors are connected in parallel. When we want a very high capacitance, we combine them in parallel, because the total capacitance for that combination will be the algebraic sum of the two, that is C1 plus C2, to give us 5 microfarads. Now, we can now discuss how it is that we combine capacitors when they are in series connection. When they are in series connection, then the current that is released by the cell from this end goes through C1 and then through C2, back through the circuit, back again, and so on and so forth. So therefore, for series connection, the same amount of current is passing through this, the capacitor C1 and C2. Now, because they are in series, the voltage across C1 and the voltage across C2, the two of them added together, the potential drop on C1 and the potential drop on C2 will give us the total voltage. Because this is the mother, this is the source. So whatever is dropped here plus whatever is dropped at C2 gives us the total. That is to say, V1, which is equal to Q over C2, is equal to V2, and V2, which is equal to Q over C2, it gives us, therefore, that V is equal to V1 plus V2. And if therefore the value of V is equal to V1 plus V2, which is equal to Q over C, then it means that Q over C is equal to Q over C1 plus Q over C2. And because the charges are the same, when we use one charging battery or one charging battery or cell, then the values of the charges will be the same. Therefore, Q over C will be equal to Q over C1 plus Q over C2, and therefore this will be 1 over C is equal to 1 over C1 plus 1 over C2. Now, I will give you an example. Example 2, when capacitors are connected in series. Now, when capacitors are connected in series, supposing we have this series connection of capacitors, the combined capacitance CT will be calculated as follows. That is, 1 over CT, as we had seen in the previous calculation, 1 over CT is equal to 1 over C1 plus 1 over C2, which will give us 1 over CT, which is equal to 1 over 2 plus 1 over 3, which is 5 over 6. And therefore, CT, remember this is the reciprocal of the total capacitance. Therefore, to get the total capacitance, you must reciprocate. You must reciprocate. That is, CT is equal to C over 5, which is the same as 1.2 microfarads. Notice that we have used the same capacitors. One was 2 microfarads, and the other one was 3 microfarads, and therefore, to calculate the combined capacitance, we find that the combined capacitance will eventually be 1.2 microfarads. Remember, in the previous example, 2 plus 3 was giving us 5 microfarads. And now, when we combine them in series, even if both of them are huge, 2 microfarads and 3 microfarads, the resultant capacitance will be 1.2 microfarads. That is to say that we have eventually gotten the objective of reducing the capacitance to 1.2 microfarads, as opposed to when we had them combined in parallel and we had 5 microfarads. That is to say that when capacitors are combined in series, the combined capacitance is lower than either of the individual capacitances. The value is lower, that is, it becomes lower than the value of each one of the capacitances. And this is key that we need to remember. We really need to remember that. Now, I would demonstrate to you how it is that we charge and discharge a capacitor. And in this circuit, we will have a source of EMF, this can be a battery or a cell. Then there is a switch. There is a switch S that can either move to point A such that the current is passing through the resistor, the capacitor, the source of EMF, and so on. And it can also, the moment it switches off from A, it can switch again to B, and immediately the source of EMF is cut, there is no connection, and now the circuit that remains is the circuit that connects the resistance and the charged capacitor, such that this is the only charge that is now in operation. Now, assuming that initially there is no charge in the capacitor at all. In other words, when the switch is on position A, when the switch is on position A, there is no charge on the capacitor. Immediately you switch on, there is no charge on the capacitor. Now, the capacitor will slowly get charged. Now, in time dt, a charge dq, remember q is equal to it, and therefore a charge dq will be equal to I dt, and it moves through a cross section of the circuit, and therefore after a certain time dt, a charge dq will have accumulated on the capacitor. Now, if you allow the capacitor to charge over a certain period of time t, what you realize, and I would like you to have such, you can construct this even in your laboratory, whereby you have a capacitor instead of a resistor, because you may not observe this with a normal resistor. Instead of a resistor, you can have a torch bulb. A torch bulb, remember, a torch bulb is made in such a way that the filament in between there is actually a resistance wire. You can have a torch bulb, and then you have the normal cells, the normal dry cells, and then a two-way switch that can switch to circuit B and that can switch to circuit A. The moment we switch to circuit A, current is flowing, is being released by the source of EMF through the torch bulb, which is now our resistor R, through the capacitor C, through back to point X through the cell, and back through the circuit. If you allow that to continue for some time, after, when the capacitor is fully charged, the bulb will light, and it will light fully. It will have charged fully, and it will light fully. The moment you switch you do the switch from that point to point B, remember there is no current now that is being released by the source of EMF, and therefore, because there's no current flowing, you switch to point B. You realize that even without any source of electricity from the source E, the torch bulb continues lighting for some time and then dims. When the capacitor has fully discharged through the resistor, it continues lighting for some time and then it dims. This is an interesting experiment that you can try even in your school laboratory, and I'm sure this will help in teaching students that capacitors can store charge, and of course it can also teach on how to discharge a capacitor through a resistor. Now, having said that, we now move to the calculation bit of it, and we reason out here that the work EDQ done by the seat of EMF, that is the cell or the battery, must be equal to the internal energy, which is given by I squared R dt produced in the resistor. during the time dt plus the increase du in the amount of energy stored in the capacitor. Now, by conservation of energy, we know that E dq is equal to I squared R dt plus dq squared over C. Since the capacitance is a constant, therefore, we notice that E dq is equal to I squared R dt plus Q over C dq. Notice that we are pulling one Q out, Q over C dq, and which can be then, if we divide through by dt, we get that E dq dt is equal to I squared R dt, and dt cancels, plus Q over C dq dt. This is important because if we consider that the current is the rate of flow of charges with time, we know current is the rate of flow of charges with time, that is I is equal to dq over dt. Therefore, in this formula that we in the previous slide, that is E dq dt is equal to I squared R plus Q over C dq dt, we replace dq dt with I. If you replace every dq dt with I, this one with I, and this one with I, and this is I squared, right? You notice that this I and one I here, and this I, because we have replaced dq dt with I, will give us, eventually, when we cancel out throughout with I, we get E is equal to I R plus Q over C. And therefore, I, if we bring all the right hand terms to the left, we subtract all of them, we get E minus IR minus Q over C is equal to 0. That is a very important formula that tells us what will happen when we discharge a capacitor through a resistor of resistance R, and if it is applied by a set of EMF E. And therefore, if we make a substitution, I is equal to dq over dt, and then rearrange the equation, we will get that dq over q minus E is equal to minus dt over RC, and then integrating these results, and we assume in the case, we assume in the case of q is equal to 0 at t is equal to 0, we will get an expression for charge and current at any time t, given by qt is equal to ce into I minus e to power minus t over rc, and I is equal to dq dt, which is the same as e over r e to power minus t over rc. And that is a formula that gives us how we go about calculating any value that we are given, that we are required to calculate given any other three values. Now, I will now introduce you briefly and quickly to the concept of resistors. Now, what are resistors? Resistors are devices that provide electrical resistance to the flow of charges or current in an electrical circuit. Therefore, they deliberately resist the flow of charges or the flow of current. Now, and there are two broad types of resistors. Now, these are linear resistors, which are also referred to as ohmic conductors. They are called as ohmic conductors from the word ohm, because they obey Ohm's law. That's why they are called ohmic conductors. In other words, they obey Ohm's law, that is V is proportional to I. That is, the amount of current flowing through a circuit depends on the amount of voltage that is given, that is being used. And because they obey Ohm's law, they are referred to as ohmic conductors, and they are also referred to as linear resistors. In other words, they will give a straight line graph cutting through the origin. Without current, there is no voltage, and it does not change. The more one increases, the more the other value increases. Therefore, they will give a straight line graph. The other type of resistors is the nonlinear resistors, and the nonlinear resistors, these are electrical devices that are altered by, for example, temperature. In other words, a good example is the thermistor. The thermistor will depend on how much temperature is applied. It will either conduct more or less depending on whether there is high or low temperature. If you put a thermistor in water and then increase the temperature of that water using some heat source, you'll realize that the resistance of that thermistor will depend on the temperature. Therefore, it is non-linear. It is a non-linear resistor because its resistance depends on the temperature. Therefore, the resistance will be given by A e to power b over t, where t is the temperature, and therefore it depends on the temperature that it is subjected to. Therefore, resistors are symbolized if you come across in a circuit a zigzag line or a rectangle, a zigzag line or a rectangle. Therefore, that is what will indicate a resistor in a circuit diagram. Now, types of resistors, you will see in a circuit a device that looks like this. In a circuit, we had seen one in the radio, in the FM radio. If you see such a device in a circuit, these are actually resistors. That's how they look like in a resistor. That's how they look like. This is a variable resistor that you can tune. You can tune, or you can change or vary the resistance using that knob. You can either increase or decrease the resistance using that knob. It is called as a variable resistor. Sometimes it can also be called as the potential divider. Now, in a circuit diagram, resistors are indicated. Like, for example, this one these are resistors. This is a resistor. This one here. These two are resistors. These ones, all these are resistors. These ones here. All these that you see, are resistors. Of course, as you can remember, in a circuit diagram, you will also find other devices. For example, we have capacitors, like we had seen in the previous FM radio circuit. And of course, there are other devices that will be for another unit, that like the transistors, the IC, and so on. There are quite a number of devices that you'll find in one circuit diagram or circuit, that depending on what is required in that particular circuit. But for our particular case here, these are the resistors that we are talking about, and it's important that you notice how they will look like in a circuit diagram. Resistors can either be connected in parallel, like in this case, or they can even be connected in series, like maybe in this case, whereby one is connected and then the same circuit passes through the two of them, or in this case here, all right? Or in this case, the circuit there is the same as the circuit that passes through that. And therefore, it depends on what it is that is required. Therefore, we need to see how to calculate the series and parallel connection of resistors. Now, this is a parallel connection of resistors. and this is a series connection of resistors. Parallel because the circuit that moves through the current that passes through the source of voltage V, the current that passes through the source of voltage V is the same current that subdivides at that point. Some of it goes through R1 and some of it go through R2 and recombines again at that point so that it goes back through the circuit again. And that is to say that this is a parallel connection of resistors, and for us to calculate the combined resistance, remember the current I that is released by the source of EMF V moves from the source of EMF, comes to that end, and some of it, I1, subdivides through R1, and another part of it, I2, subdivides through to go to R2, depending on the amount of resistance. How, remember, resistance is resistance, just like the word suggests, it is to resist. So the more resistance it offers, the higher the value of the resistance, the less the current, the less the current will flow through that resistor. And therefore, I, which is the initial current that is released by the source of EMF V, will be equal to I1 plus I2, because at that point again they will recombine again to become I, and therefore that will mean that since the potential difference across the resistance has the same value V, the PD across the resistors has the same value V. Why? Because they are being supplied by the same source of voltage, and therefore V over R, V over the total resistance, which we are calling as R, is equal to V over R1 plus V over R2, because the same value of V will be at that point R1, and the same value of V will be at that point R2, and therefore that is to mean that V over total resistance R will be equal to V over R1 plus V over R2. But remember, V is common throughout. Therefore, we can remove it or cancel or divide all through by V, and thus get 1 over R is equal to 1 over R1 plus 1 over R2. In other words, if we want to calculate the total resistance for a series for a parallel connection of resistors, then we will get 1 over R, that is 1 over R total resistance is equal to 1 over R1 plus 1 over R2. And that is to mean any number. We can have even one R3, R4, R5, provided they are all in parallel. We will use the same formula and say 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn, whatever number n is, provided they are all in parallel. Now, to calculate the value of resistors in series, we need to note and understand here that the source of EMF, the voltage V, will be the potential difference across the resistance R1 plus the potential difference across the resistance R2. And that is to mean V is equal to V1 plus V2. That is to say that if we add the potential difference across R1 and the potential difference across R2, that will give us the total voltage V, which is the source of voltage where we began, the source where we are getting that voltage potential drop from. So V1 plus V2 is equal to V. So since the current flowing through the circuits has the same value, in other words, the current, if we say the current I, supposing the total resistance for that is what we are referring to as R, the total resistance, the whole of that resistance is what we are referring to as R. So the total resistance that is passing through the two resistors R1, R2, which are combined in series, will be equal to the current through R1 multiplied by the resistance R1 plus the current passing through R2 multiplied by the resistance R2. And because the resistance, the currents are the same, that is the value of I that we are using is the same, I throughout, then it means IR, that is for the total resistance that we are trying to calculate, is equal to IR1 plus IR2, and that is to mean that because I is constant, is the same, then R is equal to R1 plus R2. In other words, if we want to get a very high resistance, we combine resistors in series. You may need to note at this point that for capacitors that we discussed in an earlier slides, for capacitors in series, the capacitance is very small. For capacitors in parallel, the capacitance is very high. Therefore, if you are teach students how to identify, how to go about getting which value they need high and which value they need low, then you need to tell them that for capacitors, it is parallel to resistors, all right? And so that how you, for you to get a small resistance, you combine in, you do a parallel connection. For you to do a very big resistance, you do series connection. For capacitors, it is the opposite. If you want a high capacitance, it is parallel. A small capacitance is series connection, and that is what will inform your students on how to go about identifying whether they need a high capacitance or low capacitance, or a high resistance or lower resistance. Depending on what they want, they should be able to you should be able to tell them that one is opposite of the other one. So we have discussed quite a number of things, and one of them that we discussed is that we discussed the concept of charge. We talked about the pioneers, those people who discussed the issue of charge. These are Augustine Coulomb, John Maxwell, and all the others. We also talked about types of charges. We said there are two types of charges, positive charges and negative charges. We also said that like charges repel, unlike charges attract. We also discussed the Coulomb's law, the relationship between the charges and the force of attraction. We said the force of attraction between any two charges, Q1 and Q2, is directly proportional to their product, and also inversely proportional to the distance of separation. We also discussed the capacitors, the type of capacitors, the four types of capacitors that we have, and how to arrange the capacitors in the circuit, either using the series connection or parallel connection. We also discussed how to discharge a capacitor, and we talked about how to discharge a capacitor through a resistor. And finally we talked about resistors and how to arrange resistors either in series or in parallel. And having said that, this brings us to the end of our today's lesson, and this is the first in a series of lessons that we shall have. In the subsequent lessons, we shall build on what we have said today. Thank you very much for listening, and thank you very much for watching me. Thank you very much.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.